Hello, everyone. This is Josh Valentine. I'm the Communications Manager with Clean Coalition. Thanks for joining us on this webinar today, the evolution of DER management systems, otherwise known as DERMS. Before we get started, just a couple of technical items to go through. The webinar recording and slides will be sent to all registered attendees within the next few days. All of our webinars are archived on clean-coalition.org and on our YouTube channel. We will be having a question and answer session after the presentation. If you'd like to submit your question and have it answered, we will try to get to it. In the GoToWebinar control panel, as you can see on my screen, there's a red arrow pointing to the box where you insert your question. It might look a little different on your operating system. That's where you should ask your questions, and we'll try to get to them at the end. And if you have any general webinar questions, email them to me at josh@clean-coalition.org. We've got a couple of virtual events coming up this summer, and we want to make you aware of them. So I'll give you some info on those at the very end of our session today. So today we have two gentlemen from Smarter Grid Solutions. Tim McDuffie is the Senior Business Development Engineer, and he has extensive experience as an electrical engineer and has integrated solar plus storage systems totaling more than 120 megawatts over the past decade. Tim chairs CLA SSA Smart Grid Committee, where his main focus is helping utilities and developers understand the full value of grid edge DER and an increasingly decentralized electric grid. Pete Malbeck is General Manager in North America at Smarter Grid Solutions. He has more than 30 years of experience working in the energy sector in North America and with utilities and regulators in over 30 countries around the world. Pete's primary expertise is in the design and technology requirements of electric utility grid control systems, deregulated power markets, and the integration of renewable energy into grid operations. So let's get right to it. I will pass it along to Tim McDuffie, and he will begin the presentation.
Okay, should be all set here. Should be seeing the first slide of the presentation. It's just an opening slide. I'm actually going to turn it over to Pete Malbeck. He's going to kind of lead things off, but the main thing that we're here to talk about today is the evolution of DERMS, or distributed energy resource management systems. We want to talk about is sort of why it's so important, particularly for the California market, and also general architectures of DERMS systems, as well as places where it's been successfully implemented, both in the UK and throughout North America. And so, the overall goal is to hopefully inform folks and let you guys know sort of what's happening elsewhere and what we sort of see coming in the California market. So with that, I'll kind of turn it over to Pete to start off with some of the introductory comments and things like that.
Thanks, Tim. Pete Malbeck here, GM for North America for SGS. Next slide, Tim. Will just a quick background on who we are. The company has been in business about 12 years. The origin story is that a couple of wind farms were trying to connect to the grid in a remote part of Europe, actually off in the North Sea, off the north coast of Scotland, in a very remote part of the grid, and the cabling and reconductoring and everything else that would have been needed to connect those wind farms would have cost about $50 million and made the project uneconomic. So the grid operators asked the local university, to take a look at the problem, and the founder of the company, Dr. Curry, worked with his supervisor on a control solution that would basically allow you to take 98% of the power, 98% of the time, working within the protection equipment and everything else of the existing grid as it existed. Those islands now export about 300% of their actual domestic load back into the system. The technology they developed was successful, and it provides a sort of additional layer of control on the grid, which allows you to integrate distributed resources of any kind onto a constrained network. Having seen that works successfully, the company was founded about 12 years ago. If you go to the next slide, Tim, I'll just point out that today this technology is used by the majority of the DNOs in the UK to connect and manage all of the distributed resources, intermittent distributed resources that are being added to the networks there. I think everybody knows the UK has a very aggressive requirement to get to essentially defossilize as soon as they can. The latest project over there is with UK Power Networks, which covers the whole of southeast of the United Kingdom, including the City of London, about 20 million people. And these systems are being used for that. There's a selection of people in North America on the left side of the screen. The company's been working in North America for about 5 years, and with the companies that you see. I'll just mention some other use cases that, and we can move on to the sort of main part of the presentation. This background is just meant to sort of set the stage for where this all comes from. Having a use case that enables you to manage the constrained interconnect and add additional resources to that without having to go through the tremendous costs of network upgrades that can be incurred. Once you're able to do that, it introduces a whole set of other use cases around things like microgrid operation, flexibility services with demand response and other things, and just any number of other types of ways of utilizing distributed resources to actually become an asset to manage the grid, as opposed to a intermittent and difficult to manage liability out at the grid edge. Some projects like the one at Tucson, which was done with EPRI, was to demonstrate both front of the meter and behind the meter technologies. The things in Canada are mostly to do with microgrid operation. That's obviously becoming a big thing in California. The work at Con Edison is to integrate 4 batteries into around New York City onto the network, and to enable them to both play in the New York ISO markets, and to make the owners of those enable them to have access to those markets to drive revenues, and at the same time allow Con Ed to step in situations where they need to use the battery in some sort of override situation for local distribution support of some kind, which is quite a complex problem, but again opens up additional use cases and revenue streams for the application of these distributed resources. We can talk a lot more about all of this, and we do have a lot of particular use cases that we'll try and touch on in the next sort of 20 minutes. And so with that introduction, I think I'll hand it back to Tim McDuffie, and he can continue from there.
Sounds good. Thanks, Pete. Right now, we'd like to take a few minutes and just talk about DERMS technology in general, because it's a new term to a lot of folks, and it's sort of a buzzword that just kind of keeps getting thrown around. But before I do that, I kind of want to talk about also how I ended up at Smarter Grid Solutions, because I think that sort of evolutionary process is something that a lot of folks, particularly in the developer world, can relate to. So I started off in the California market with a company called Calcom Energy, where I was tasked with building an engineering department from the ground up. And that was in 2014. And what I realized very quickly is that the real challenge isn't necessarily the, behind or inside of the fence design, but rather the interconnection. Because when we started, I would say probably 10% of our projects were being delayed or were hit with relatively large interconnection costs. you know, that was 2014, 2015, 16, 17. We saw it, you know, increase to maybe 40%, 50%. And by the time I left in 2019, it was easily 60% of our projects. And these are relatively, well, I'd say medium-sized DERs between 500 kW and 5 megawatts. And as part of my job there, you know, I was integrated into a lot of the working groups, whether that's working groups 2, 3, and 4 within California Rule 21, the Smart Inverter Working Group, as well as the ICA Working Group. And all of this was to hopefully allow for more DER to be integrated onto the grid without the need for substantial upgrades. And what I came to realize, particularly towards the end of my tenure at Calcom Energy, was that you know, the tenability of, I'm just going to switch ahead to this one because this is probably a better slide. You know, the ability for us to manage high levels of penetration, you know, really depends on a regulatory environment and also a mentality from all stakeholders as to how we want to get to 100% renewables by 2045. And so the question is, you know, there's two basic paths. They're saying, okay, we can maintain the current path, which is to trigger an upgrade with a review study, and then do that upgrade to whatever cost, whether that's ratepayers or anybody else, and then, you know, continue along, you know, that sort of that cycle, which at some point will begin to impact the amount of DER that can go onto the grid, because as you can see on this slide here, or actually both of these, or both of the images or the graphs on this slides are pretty stark. So what you have on the left is the SCE RAM map. Now this data is a little old. I think it's from 2018, but you can't get this viewpoint anymore when you look at the ICA map. But you don't have to be an electrical engineer to look at this and realize that this is just a large portion of the Central Valley where there is no capacity whatsoever, or very, very limited capacity. And when you look on the right, I think this is an even more stark indication where, you know, grid saturation is starting to become an issue, because this was the first run of PG&E for their ICA, which is the integration capacity analysis, where they basically define hosting capacity throughout their system. And what you'll see here is that the large bar on the far left-hand side of this table shows that over 80% of their system, you cannot add more than 100 kilowatts without triggering a detailed study. And if you're not familiar with the detailed study, a detailed study is where you, you know, become, you know, you go into a much longer review timeline, as well as a much, just a larger chance of triggering massive upgrades. So 80% of the PG&E system is such that you can't add more capacity to it without triggering a very large upgrade. So then that becomes the question of, well, what do we do about all of this? And so that's where DERMS comes in, because what DERMS does is it allows the utility the access that's needed to your system to operate it, as opposed to, or to manage your DER, as opposed to using upgrades. So traditionally, you know, you run an interconnection study, it triggers an upgrade, and then you have to go back and pay for that upgrade, whether that's a reconductoring, transformer upgrade, direct transfer trip, whatever that is. And you know, you're usually having to wait very long timelines, particularly if it's a substation upgrade. You're looking at probably 3-4 years. I should say 2 to 3 years is probably a more accurate way to look at it. And with DERMS, you're not managing to the exception, or I should say you are managing to the exception, because when utilities run these interconnection studies, they push and pull and stress test their systems through their simulations to try to find where they can essentially, you know, have the lowest common denominator breakdown. And what DERMS does is it says, okay, as the system starts to approach this calculated point, which is very, very rare if it happens. And if it happens for maybe 10 or 15 minutes over the course of a year. As it starts to approach that calculated breakdown point, the system, the DER, takes action to prevent it from ever crossing that threshold, whether that's voltage, whether that's current, frequency, whatever that is, or it could even be capacity of a transformer. It could be islanding, it could be anything. And so it's essentially a system that allows DER to take automated action to prevent unnecessary or undesirable grid conditions. So the slide you're looking at now is why DERMS, why now? And it kind of highlights the benefits to 4 of the major stakeholders throughout California. So when you look at the impacts to regulators, I'm sorry, just a second. Getting into architectures in just a moment. When you look at the impact to regulators, DERMS can really help to expedite the path towards 100% renewables, which, as we all know, is the path that California is on to get there by 2045. And it does that through expanding hosting capacity, because conductors that were previously limited by conductor sizing or voltage or anything like that, can now be expanded through the use of DERMS without additional hindrance to the electrical grid or additional costs that are prohibitive. When you look at grid operators, folks could say, well, how does PG&E, or folks will say, how does PG&E or SC or the other major utilities feel about this? And, on one hand, they look at it and they say, well, that's cool, but that's the future. On the other hand, when they start to realize the visibility that they get, as well as the additional control measures, the light bulb starts to go off where, the need for this, or the capabilities that are unlocked by it, become very, very apparent. And, there's usually that threshold where it goes from, in their minds, of the future as to what we can do now with DERMS in the present. When you talk about aggregators, aggregators can, I should say that, there's been sort of a misconception where DERMS and aggregators could be competitors in some instances. But in reality, DERMS fits, if you think about from the grid edge going towards the transmission network, DERMS fits in between the aggregator space and the ADMS space. So we provide that link as well as a layer of automation to sort of aggregate the aggregators before it gets to the utilities. And then DER developers, as we spoke about, we can help clarify and stabilize PTO timelines and also avoid unnecessary mitigations, that could potentially kill a project both financially and just technically as well. The last thing I'll say before I move on to the architecture of a typical DERMS is that one of the major things that's been successful for us as we've implemented DERMS throughout the UK and also in broader North America is that it's offered as an option. It's not saying you have to do this. It's offered as a 3 options sort of thing, and that's what's happening right now in the UK. And Pete will speak to the actual nuts and bolts of it a little bit better a little later. But the option is do the traditional upgrade, or you can have what's called a managed interconnect. And the managed interconnect is essentially interconnecting and giving a little bit of control to the utility to allow them to manage whatever constraints identified during a typical study. And then the other option is just interconnect with no upgrades, which again is becoming more and more of a rarity, I would say, throughout many of the different municipalities that are out there. So a layered approach to control. We're using our proprietary equipment in this as an example. I would say a lot of the DERMS companies out there have a very similar sort of approach. Everybody does things a little bit differently, but we're using our equipment, but we're trying to speak more today about generalities and to be more informational about DERMS and how it all kind of works together. So 2 major components of DERMS. You have a centralized sort of brain, if you will, which is takes information from the grid edge and runs through different layers of control and optimization. So for example, if you're trying to manage voltage at a certain point, the actual brains of the DERMS system can be deployed either in the AWS cloud or within an RTU within a substation that takes in all of the points from the grid edge and makes a decision and then sends commands back out autonomously and in real time out to the grid edge. And the idea being that that centralized sort of node is that one piece of interaction to the utility, is the one point of interaction to the utility, and sits usually within their equipment, which makes the utility very happy because security is always one of the first things that comes up in these discussions. And then when you look at the grid edge, that's where we have things where you have localized site DER control. Now, there are a number of different site controllers that are out there. We have one that you see here called A&M Element, but the overall idea is to have something out at the grid edge that can provide automation and provide a basic level of functionality should communication to the centralized controller be lost. And so this is a very high-level overview of a typical utility DERMS. And you'll see some of the different components that I spoke about earlier, where you have, the centralized bit that's either hosted in the AWS cloud at the top. As a matter of fact, I'm going to try to use one of these fancy functions here. Let's see, Spotlight. There we go. So I don't know if you guys can see this or not, but up here at the top, this is that centralized system. Ours has a dual redundant core and also a dual redundant hub. So that's just if one fails, it can automatically switch over to the other. It also speaks to interfaces with the utility. And this would be something where instead of having to switch between, our user interface and their ADMS, it's integrated as to one big package so that it's not something that's clunky and that they have to switch between. And that's one of the things that was developed early. And a lot of DERMS systems operate in that fashion. And then you can see also utility systems where we have portals, modeling, all these different inputs that then all feed back into A&M or to the centralized DERMS system, which is A&M Strata in our case. And then you'll see here where this is just an example of a singular DERMS, a single DER that's been interconnected, but in reality, this could be up to hundreds or potentially even thousands of DERs, depending on the size and the substation. And then if it got too big, we can even link, essentially have a master sort of DERMS platform that then controls subservient, other platforms that are out there, so that you can sort of network the whole thing together. This next slide is a little bit more intense, obviously, but it's pretty interesting because it hits on what Pete was speaking about earlier, and that was the work that we did with Con Edison. And what's interesting about this is the amount of integration that you can see. It's intended to do two main functions, and that is first provide optimization and take in dispatch controls from a third-party financier, which in this case is the New York ISO market, and provide those as a basic operating system for day-to-day operations. Now, the part that's unique about this is that it also integrates utility systems. So you'll see where the SCADA, ADMS, and the EMS is all controlled, and then there's just one single user interface down here. So that if and when Con Edison decides they need to take control of this site for grid stability or whatever the condition is, then they can interact with their existing user interface and take control of these batteries. And it's a very, very interesting and very kind of forward-thinking way to do it. And quite frankly, the tech side of it was relatively easy compared to the regulatory and contracting side, which when you're trying to marry, a financier with the utility and get them to work harmoniously, it's a very, very difficult thing to do. It's very challenging. but it was able to work. And these have been up and running now for, I think we just finished the last of the 4 batteries earlier this year. So it's fully deployed. A&M Strata, I left these slides in here. Again, we just want to speak high level about it, but A&M Strata is the centralized platform that provides automation and control. And then A&M Element is just the grid edge device that works to provide localized control, behind the fence. Let me turn this little thing off here. Actually, I'll leave it on. So this slide just sort of speaks to some of the different applications of DERMS, because what we found is that, just using it for expanding hosting capacity or, things like that, or traditional sort of ideas of upgrade avoidance, really sort of kept it into a very predefined box. And what we found is that as soon as we started implementing DERMS, the question became, well, what more can we do with it? And we were able to determine that, microgrids are a very close cousin, or I should say microgrid controls are a very close cousin to a DERMS system. Because if you think about it, the exact sort of things that you need for a DERMS are the same things that you need for a microgrid controller, particularly if you're doing it at the substation level, or if you're doing it at the plant level, if you've got a primary feeder going into a plant. You need everything to be interconnected, you need everything to be working together, and you need it to be all automated and controlled under one system. And a DERMS controller provides that level of control at the microgrid level, and also provides the integration with utilities that they like, because obviously utilities, they don't like having things energized on their system that they don't know is energized, and with good reason. You can relate to that.
Yeah, just to interject something. Traditional microgrids that were just diesel operated, essentially systems that just switch to backup diesel when the grid disconnected. That's really not what we're talking about here. We're talking about microgrids today that people want to operate with intermittent resources such as solar and wind, and integration of batteries and things, which obviously is the complicating factor beyond the traditional sort of grid isolation techniques that have been around for a very long time for hospitals and campuses and things. So what gets interesting in this is the need for the sort of layers of control that we've been talking about when you're working with distributed resources, and these are particularly appropriate to things like remote communities that want to avoid using diesel, or at least minimize the use of their diesel, and still operate a functional microgrid that can connect and disconnect to the main grid when needed, and operate even with the intermittency of the resources that they have. And so it's the complexity comes often in managing the dispatch between the availability of the solar, the wind, when should you run your batteries, and when should you just use the diesels. So that's I just wanted to put that in, Tim.
No, that's a great point. And I mean, it allows for that optimization during non-islanded events, and then also an easy switchover, or a close to seamless switchover to an island when needed. And so the idea is that the end user, they might see a little blip in their voltage or something like that, but by and large they can't tell the difference between whether they're on an island or whether they're connected to the grid. And all of these different pieces, the DER, like Pete spoke about, particularly renewable stuff, can be married with diesel generators, any sorts of, when we think of DER, we typically think of solar and solar plus storage, but in reality, it's solar plus storage plus fuel cells plus diesel generators, and all these different things that can be used together to form and provide services when it needs to operate in an island. Just a moment. I'll move sort of quickly through these because I want to get to the use cases and speak to some of the specifics. But renewable and distributed generation, we spoke to that. We spoke to how that integrates with the integration between the utilities to the grid edge, and then also the ability for developers to avoid upgrades. Energy as a service, we touched on that just a second ago with the optimization that's available, and the different services that can be provided by microgrid devices during non-islanded period or during non-islanded timescales. And so that's just integration with wholesale markets or some of the more traditional load shifting, generation shifting, those sorts of things that you could expect out of any sort of DER that's out there. Virtual power plants, this is again more geared towards the utility value, but the idea is if you have all of these, say you have 1,000 DERs connected to your system, well, the utility doesn't want to look at 1,000 different DERs, particularly if you have multiple DERs behind the same point of interconnection. It's just too much data. And so what a DERMS system allows you to do is aggregate a lot of these, I should say aggregate above the aggregation level, a lot of these different resources into one block of operation. And then that one block of operation can then be integrated and controlled by the utility operators as needed, so that it's not 1,000 different data points. It's just one thing that does exactly what they needed to do. And we spoke to microgrids. Not much to really talk about there. So now we'll get into some of the case studies. And these are examples of some of the different projects that we've done, throughout both. We're focusing mostly in North America on this, although we do have a pretty exciting one that's happening right now in the UK, as well as a couple of really neat opportunities that we're working on in Canada as well. Pete, do you want to speak to Avangrid or the FICS?
Step through these quickly. Yeah, Avangrid is an example of a utility that was interested in this flexible interconnection and studying, how that would work. So they were a sort of early mover in North America regarding this. I think everybody's familiar with the New York REV work that was started about 5 or 6 years ago with the view to looking at how the use of energy as a service ideas like demand response and other things could be integrated with flexible interconnections of distributed resources. And now, of course, batteries. 5 years ago, batteries were too expensive to really consider in this, and today, of course, they're not. So there's been some fairly rapid developments just in the last year or two. But the Avangrid's projects are to do with the ability to it's mainly hosting capacity, this particular project, which is figures that the utility would have considered constrained before, because under worst case conditions of load and various failure scenarios, they would not allow additional resources onto the grid. And they were studying the idea that with this new layer of technology, that they could expand that capacity a great deal and do so safely. So again, all of this technology is developed with the protection engineers of the utilities. It was originally developed under the watchful eye of the protection engineers of the Scottish grid. It works within the protection scenarios of the equipment. And it basically, again, it's a look at what do you have at your disposal on the particular feeder to keep things operating as optimally as you can. And unlike sort of brute force protection equipment, which breakers and switchgear and fuses, which tend to need to be hard reset after they've activated, this is a software control system that will bring things back to full production as soon as that's possible, which again is a big boon to developers, because it means that you may be curtailed for some very small period of time, but as soon as grid conditions can turn to normal, you're back up and running completely. So next one, Tim. We talked about Con Edison again, the batteries project there. It was fairly unique when it was started. It's now, people are looking at this in a lot of different places. Again, it's the idea that you can have multiple people interested in the way a particular battery is used. There can be someone who's financed the project. There can be the utilities obviously got an interest in what's going on. The people, there may be something behind the meter locally, buildings which are interested in curtailing, their demand charges. there can be a lot of different things happening. And of course, what people have to remember is that a battery is not a generator. The only advantage you have is arbitrage between the price it costs to charge the thing and the what you get back when you're dispatching it. So it really narrows your window of financial opportunity a great deal. But nevertheless, you know, we found that you know, this is something that the ISOs all over the country are very interested in looking at. How are they going to manage a very large increase in the amount of battery storage onto their systems? And as Tim said, actually 2 of those are in operation. Tim, the other 2 are completing their site tests as we speak. Next one. Tucson, again, an interesting project because they're looking at the home of the future. So particularly in the desert Southwest, there's a realization that for those lucky people, and we're not, you know, there is a whole financial argument about people that have their own home, their own rooftop, their ability to go fully electric in the house, to generate a great deal of their own power from their own roof, which now extends to charging their own electric vehicle through power packs on their wall. You know, utilities in the Southwest and places where there's an extreme amount of sunlight are seeing a lot of penetration, people interested in this concept of essentially going off grid. And of course, this is nothing new. It's been around a while, but TEP wanted to look at this combination of controls of what's going on inside the house, what's going on behind the meter with the solar generation from the roof and the batteries, and what's going on in front of the meter in terms of other things that are happening. But the concept of this, particularly in hot, sunny climates where you're going to be essentially a self-contained unit with the combination of EV, all electric appliances, but nevertheless needing backup support from the utility. And again, this is not new. It's been around for a while. Arizona's been through, over the last 5 years, a lot of debate about who pays for the grid to still be there. When all of the wealthy people can disconnect from it and people living in apartment blocks don't have that luxury. So it wasn't really to study that. This project was much more about how the controls work and what the utilities' visibility into these things are going to be. Again, there's some publications that EPRI made out of the project, and that Tucson have also publicized this, that people can find if they're further interested in the results of that. And finally, we thought we'd mention DOE-funded Project EASE, which is finished 2 years of its 3-year project lifestyle. But again, a utility like Edison looking at thousands of connection requests for solar every month. This is something that Tim, living in Southern California, has been aware of, particularly his work at Cal SSA. It's how to manage that process, how to allow more distributed resources at this scale, 10,000 or more, you know, rapid deployments coming onto a utility network, you know, and how to meet the state mandates for getting to renewables while maintaining a stable and operational grid. This project looked at both how to automate the interconnection process, and then what were the factors around just managing very high penetrations of DER onto a grid. And obviously Edison is one of the places that's most affected by that. And I think that's our use cases, Tim. Oh, except for UKPN. So UKPN is again the model that is used in the UK with DNOs, which are somewhat different structure to the way that the still to some extent vertically integrated utility systems work in the US. There was a very interesting seminar quite recently with former FERC Chairman Wellinghoff and people from Cal ISO actually talked to the UKPN project managers. They were part of that webinar. It's about a month back. You can look it up. It was largely to do with, is this the future for distribution network operation in the US? Because things do tend to be, appear to be trending that way. And again, this is a major rollout where one of the across an entire utility service area that encompasses a giant city like the City of London, but believe it or not, even though this is overcast all the time in the UK, there's an enormous solar deployments there, and other kinds of DER, everything to biodigesters and everything you can possibly think of. But the idea here was that we integrated with a network modeling system at the same time, which in fact most of this deployment feeder by feeder does not require. You don't need to, at like the transmission level, you don't need to optimize the entire transmission system in one pass when you're trying to optimize the operation of DER that are connected, a couple of transformers out on the distribution network. It's a different approach, but in this case, there's a combined local optimization on a particular feeder with a sort of more global approach to how to operate a large network, which requires the traditional approaches to being able to model and predict what's going to happen across the entire structure of the network at a whole, which is the traditional, as most people will know, transmission approach to management of the network. So again, this project's received a lot of visibility, and it was something that Wellinghoff's new organization was particularly interested in, held a very, very informative webinar on recently, again with Lorenzo Christoph from CalISO as one of the principal participants. I think we're sort of out of time, and I think we've just reached it, Tim, and I'm not sure if our organizers are happy with how much time we've taken, but I think we're about on schedule.
Yeah, I think we are. I think we're at the Q&A point. So yeah.
Thanks so much, Tim and Pete. Before we get to the Q&A, I just wanted to mention that the Clean Coalition is all about renewables-driven microgrids. Two great examples of what I'm talking about. I'm showing on the screen on our website, Goleta Load Pocket Community Microgrid. You can find that under programs on our website at the very top. And you can find out all about it on this webpage. And our work with the Santa Barbara Unified School District. A great overview is written about in an article in Solar Power World that came out a couple of months ago. You can find that on our website too. If you go to the media section, news and press under media coverage. And if you wanted to email me for any of this information, I'm glad to send anything out to anybody. Again, that's josh@clean-coalition.org. So let me change presenter back to you, Tim, if you wanted to reference the presentation in any of the questions that we're going to be asking you. So I'll give that back to you.
All right. Let me just pull this up.
And like I said in our discussions before the webinar, feel free, Pete or Tim, to take these questions. If you both want to chime in, that's great. So the first question that we have is from Tom Roberts of the CPUC. Do SCE, SDG&E, and PG&E have SGS DERMS? If not, how are they your customers?
Yeah, I'll take that, Tim. So it's a good question. SCE, we worked on the integrated grid project for several years with SCE, and we've been working on the Energize project with them for some time. So in terms of customer, it was really the integrated grid project. They are the prime contractor. We are their customer for the DOE work. San Diego, the work was a study to do with the management of strata of DERMS interconnections. In other words, how do you group and manage groups of these things together? That project was completed about a year ago. PG&E, the work at a different project is in the lab in San Ramon. The systems are installed in the PG&E labs there, but that project is again run through the auspices of Lawrence Berkeley and with the University of California, Riverside. But the host utility is Pacific Gas and Electric for that job. I hope that answers the question. But they do not the answer is that they are not fully deployed operational on the grid strata systems.
Great, thanks, Pete. The next question comes from Michelle Thompson. Michelle's a regulatory analyst at CPUC. On the slide, specific slide, why DERMS, why now? She's referencing, what is hosting capacity under regulators and what is PTO under developers?
Tim, I'll take hosting capacity. Well, you take both of them, Tim, go ahead.
Yeah, sure.
Capacity. I mean, because I try to keep it simple, that's simply the ability of the existing grid infrastructure to support the interconnection of additional generation without needing upgrades. So the grid is typically overbuilt. There's typically, if someone wants to add a small solar farm to the grid at close to an existing substation, there is usually the capacity to do that. Not always. As things reach saturation, the hosting capacity reduces, and to add more distributed resources would take an upgrade in the grid.
Yeah, and PTO is just permission to operate, and in the developer world, that's the ultimate goal, obviously, and it's usually a milestone. Well, it's always a milestone for any sort of project that you have out there, whether it's a structured finance project or if it's just a cash-driven project as well.
Excellent, thank you. The next question comes from Sarah Biabani. Sarah is asking, are UK DNOs privately owned and run?
Yes.
Pete, I'll let you take that one.
Yeah.
There you go.
They're typically investor-owned operations, like in the operations here, and they can be they're not state-owned facilities, if that's what the question is.
Great, thank you. The next question comes from Norman Wilson, a principal consultant at Rex Wilson LLC. Norman is asking, what is the financial model or economics that would be useful for a developer?
I'm happy to take that unless you want to, Tim.
No, go for it.
Well, so the economic model, it really boils down, and this is something that is an issue for developers. So developers typically have financial people that look at this wind farm or solar farm is scheduled to generate this amount of power over this period of time. They model weather, they model cloud impacts, they model everything. They try to figure out how much are they going to generate out of this. They have future predictions of price modeling, price curves, how much it's going to be worth, and so on, to look at the economics of the DER development overall. If there is a requirement for a grid upgrade, that can be a lot of money and it can take a long time. It can delay the project by several years. So the economics comes back to, if you get a managed interconnect where you can be curtailed at times, how much will that curtailment be? How much will it cost you? And how much do you save avoiding the grid upgrade? And how much do you save in terms of time to getting your project to market? And those are just two of the factors. There are others, but I don't want to overcomplicate it. That's the typical financial model trade-off between what's called a managed interconnect and a one where the only thing that's going to manage your output is how much sun or wind is available at any particular time.
The only other bit I'd add to that, and it's just based on my experience in the developer world, to Pete's point, is that it is possible to manage curtailment, or model curtailment and run through simulations to understand the financial impact of curtailment based on grid conditions. So it's the same as if you're trying to model weather. It does add a level of risk. However, it's manageable risk, and it's the long-term financial return compared to short-term capex expenditures, as well as delays to PTO that could happen with upgrades. And it doesn't always pencil out, but as saturation becomes more of an issue, the financial prospect of it becomes more and more relevant.
Yeah, I should have added, Tim, that it is possible for us, by studying the situation and how close you are to the saturation limit, to be able to produce a fairly accurate forecast of not only how much will you be curtailed, but under what conditions and when. And they can build that into their financial modeling.
Perfect, thank you. And the Trudy Wang from Gila Technologies is asking, how are benefits dispersed to the end users in the aggregation level and microgrid level market use cases?
So
yeah, Pete, you want to?
Well, I'll take it initially. It's a very good question. It's a cause of a great deal of debate amongst Ofgem, for instance, in the UK, the regulator, who pays for the upgrades and who benefits. For instance, obviously the case in the US has been that if a first-on developer of a farmer's field in New Hampshire has paid the utility to upgrade the grid, and that produces capacity for other subsequent people to come in, why should he pay for all of it? And they get the benefit of it. And then secondly, there's a case of if the utility is going to upgrade something, how does that go into the rate base and benefit their consumers on that basis? And that's a very good question, but it's going to be a very long and complicated answer to that, I'm afraid, if we go into that at this point.
And speaking to microgrids, the point that was brought up about being able to provide financial incentives is absolutely, it's a very, very good point. And the reason I say that is because that's a lot of what we're starting to discuss right now through the microgrid proceeding within the CPUC. And that's sort of the next thing on the docket is how do you incentivize and make it more financially viable to develop microgrids so that there's resiliency during PSPS events, which are public safety power shutoffs, while also making it allowing for greater participation during non-shutoff events, just to increase the economic viability. Some of the different ideas that are out there are, creating an incentives for folks who can, even if you don't participate in the SCHIP program, let's say you went to apply for it and the funds are already depleted, or you've been otherwise, you're not going to be able to participate in it, but using the greenhouse gas signal from the ISO to incentivize people to charge and discharge during different periods. It's just one example. It's not something that's set in stone by any means, but there is still a very broad discussion as to how we incentivize folks, using some of these different, or I should say newer controls and integrations that are out there to utilize these microgrids to their full capacity in the future.
Great, thank you. Albert Chan, also from Gila Technologies, is asking, can you describe or re-describe why you separate utility DERMS from fleet DERMS? How separate are they in terms of types of customers, needs, and features? And feel free to truncate this from what was it?
Yeah, no problem. I have a tendency to
Tim, let me try and summarize that one.
Yeah, go for it, Pete.
So utility DERMS, the way we think about it, is a utility like PG&E or Riverside Public Utilities or someone in California deploying a sort of global license system across their territory that integrates to their existing control systems and allows them to run and operate all of these devices. Fleet DERMS, in some of our descriptions, applies to the sort of as Tim was talking about, virtual power plant aggregation of multiple things. For instance, if a project developer deployed a group of solar fields or a set of batteries around a grid, the utility might want to look at them as one asset, but the operator might want to disaggregate them into a fleet of separately operable items. So that's really the only real distinction there. And a fleet can also be multiple different types of DER integrated into a single sort of operating whole. And it's just a differentiation between who is sort of managing the group of the assets. Is it the utility managing their entire distribution network control area, or is it the developer managing a fleet of projects that he's developed?
Great, thank you. Lloyd Huber is an architect with LWH Architecture, and he's asking, how does deployment timeframe of DERMS correlate to deployment of additional infrastructure requirements? And can you please comment on likely additional 36% energy demand over the next 2 decades in urban centers like New York City?
Well, let me, so the fastest deployment we ever did was 35 days, which is sort of extreme case. Typically, a project like this will go through a study cycle. You need to look at the feeder, what the impact on it is. You need to assess the curtailment levels. You need to do those things, and then you need to deploy the system. So that whole process, 3 to 9 months. Whereas if you're going to upgrade the grid, the utility life cycle on that is typically the first year is a study problem, the second year is getting it into the rate base, and the sort of end of the second year or even into the third year is actually the build out. So we typically shorten things by somewhere between a year and 18 months using this approach. But it's very dependent on the particular situation.
Great, thank you. All right, so Eric Vyum, who's a chair at San Luis Obispo Climate Coalition, is asking, are DERMS an opportunity for non-wired load-serving entities such as community choice aggregators?
Yes,
Yeah.
the short answer is absolutely. And when you're looking for non-wire alternatives and you're looking to serve load locally, DERMS is absolutely sort of that central nervous system of, grid edge, command and control, going back to a centralized thing. Integration of load is just an offshoot of that. So whether or not you're saying to, generate and balance load, or generate to a specific load value and then balance the two, which is sort of, I think, what the question is getting at. That's absolutely something that DERMS is capable of doing.
And I'd just add that Rocky Mountain Power has published a lot of work on, the ability for, all of the sort of tribal entities, as Tim will tell you, we work with tribal entities in the US and other municipals that can be very tiny electrical operations, especially on the eastern side of the country where there are hundreds of municipal operations where they would like to convert some brownfield factory or something into a source of generation. Some years ago, FERC relaxed the rule on having to buy 85% of your power from your the PPA, the power producer that you were signed up with, to allow you to enable you to do more green generation of your own inside your own control area. And that's exactly the situations where systems like this can be extremely useful, because they can reduce the cost of all of that, and they can give you the necessary interfaces to the transmission provider or the utility provider that keeps everything secure.
All right, thank you. All right, so we've got 2 more. From Arian, General Manager at Suntech Power Development America. Artie's asking, which utilities already work with you and accept this approach that you are pointing out?
That's a very good question. The place where you'll have most success is in the Northeast at the moment. Places like Avangrid, Orange and Rockland has projects that we're working on, Central Hudson, but it's reaching the point of acceptance, but there's still we're still at that point where we do have some regulatory headwinds. For instance, the utility are not generally incentivized to get more assets onto the existing infrastructure. This is a very perverse situation where utilities, especially IOUs, provide a return to their investors through the addition of more infrastructure. They're not allowed to make a profit off the actual power delivery. And we are perversely incentivized in the way that squeezing more out of the existing assets like this actually runs counter to the way that utilities are able to make money. But there is in general, just about any utility in the country, we'd be happy to go to developers with and talk to them about it. But there's really quite limited number that this is just something you could immediately work with them on. You can do it in a lot of the utilities in the northeast of the United States, but not yet in other parts of the country.
The only thing I'd add is that we're always open to speaking to any utility or any developer about any opportunity, because a lot of times when you speak to utilities, particularly in non-heavy areas of population, you'll run into folks who've never heard of it and never thought of it, and it just seems very new. And so just having that discussion, even if it ultimately doesn't go anywhere, is extremely important, just to get the word out there, and hopefully change some hearts and minds as if we don't have those discussions now and we wait 5 years, then we've sort of pushed the overall timeline back. So we're always happy to have those discussions and just do what we can to help developers in those situations, and hopefully hopefully it comes through.
Great, thank you. And final question from James Farrard, who's the Director of Energy Markets at TID. Is it possible to get more detail regarding the commercial arrangement among my ISO, Con Edison, and Microgrid?
It will be soon. There's none of this is sort of secret, but while it's under development, the utilities in New York ISO are sort of reluctant to release information until it's all cleared their process for announcements and other things. So I would say that we'd be happy to provide what we can on that within the limitations of what we're allowed to talk about under the rules of both the ISO and Con Ed. So you could contact us separately, and we'll see what we can do for that.
Okay, great. All right, so thank you so much again, guys. And I just wanted to reiterate that Clean Coalition, we are renewables-driven, microgrid focused, and we're highly appreciative of you both joining us for this very excellent webinar and very informative on the evolution of DER management systems. And before I officially close out the webinar, I just wanted to go on our event page. We have a couple of virtual events we're taking part in through the rest of the summer. One in particular is something that I mentioned earlier about the Clean Coalition's work with the Santa Barbara Unified School District. There's an article about it that was written a couple of months ago and published in Solar Power World. If you want a link for that, just email me, josh@clean-coalition.org, or you can go on our website in the media section. And also a good example of our renewables-driven microgrid work is the Goleta Load Pocket Community Microgrid. And we have some great information on that on our website. The Santa Barbara work is going to be highlighted on July 8th in the Community Energy Resilience series that's going on through August, I believe, and you can get some more information about that on our website if you go to events and then upcoming events, and you just click on here. And so without further ado, actually, I don't think I was showing my screen. So here we go. Let me back up. So this is the Clean Coalition website. This is the webinar and events listing. So you just go there and you can pull that down from events, upcoming events, and then go to the Goleta Load Pocket under programs. It's right there. And the article I was referencing. So once again, if you have any questions, email me, and thank you so much, Tim, and thank you so much, Pete, for your presentation. I hope you come back and do this for us again in the future.
Thank you.
Thank you very much.
All right, have a great day, everyone.